In about 2 seconds, a machine buried under the deck of an aircraft carrier takes a fighter weighing as much as a loaded truck and throws it off the front of the ship from a standing stop to flying speed in a distance shorter than a soccer pitch. If it puts in too little energy, the aircraft goes off the bow below the speed it needs to fly and drops toward the water in front of a ship that cannot stop. If it puts in too much, it can tear the nose gear out of the aircraft. It has to be right every time for every different aircraft, dozens of times an hour. And here is the part that stops people who work with machines for a living. The system that does this, the steam catapult, is one of the most wasteful major machines ever put to sea. It throws away the overwhelming majority of the energy it uses. Engineers have known this for decades. They built a replacement that fixes it. And in the summer of 2026, the United States Navy decided to go back to the old wasteful one anyway. Why a machine that squanders most of its energy beat the efficient machine meant to replace it, and what that says about how these ships are actually built, is the subject of this. Start with the assumption almost everyone carries, because it points you in exactly the wrong direction. When people picture the hardest problem on a carrier flight deck, they picture power. Getting enough force to fling a 30-ton jet into the air looks like the whole challenge, and it is natural to assume the better machine is the one that makes more force, or makes it more efficiently. But raw force was never the difficult part. A steam catapult has force to spare. The difficult part is control. The difficult part is delivering a precisely metered amount of energy, tuned to the exact weight of this particular aircraft on this particular launch, in a curve that accelerates it hard enough to fly, but never so hard that it breaks, and doing that identically, launch after launch, in salt air at sea, with the deck pitching, for 40 years. Seen that way, the story turns over. The catapult is not a power problem that happens to need some control. It is a control problem that happens to have plenty of power, and the reason the old steam system survived is bound up in that distinction. There are 4 things worth understanding to see how it works and why it endured. What the launch actually demands of the machine, in numbers. How the steam system meters that ferocious energy without destroying what it launches. How the whole thing is built into the ship and where its deliberate weaknesses are placed. And why the machine built to replace it, better on paper in almost every way, could not simply take its place. 4 systems, and behind all of them a crew on the deck who set a number by hand and have seconds to catch it if it is wrong. We will take the machinery as it stands on the ships in service today, and every figure here is drawn from the published and declassified record. If this is the kind of thing you would give an hour to, the channel exists for exactly this, so consider subscribing before we go below the deck. We start with what the launch actually costs. Understand the numbers because they are what makes the machine so strange. A carrier's steam catapult on the current ships is a track running the better part of 100 meters beneath the flight deck, and in that distance it accelerates an aircraft that can weigh in the region of 30 tons to a speed of well over 200 kilometers an hour. That happens in roughly 2 to 3 seconds. The energy involved in a single shot is on the order of 95 megajoules of useful work delivered to the aircraft, and to picture what that acceleration feels like is comparable to taking a pickup truck and driving it from a standstill to highway speed in about 1 second. That is what the airframe and the pilot absorb on every launch. And now, the number that reframes the whole thing to deliver that 95 megajoules to the aircraft. The catapult consumes something like 600 kilograms of steam per shot, and the overall efficiency of the system, the useful workout compared to the energy put in, sits at roughly 4 to 6%. Read that again. 94 to 96% of the energy is not delivered to the aircraft. It is lost as heat, as friction, as steam venting off the track, as the energy dumped into stopping the pistons at the end of the stroke. The machine wastes almost everything it uses. On land, in a power plant, an engineer who built something 4% efficient would be dismissed. At sea, on a carrier, that same machine launched hundreds of thousands of aircraft across 70 years and became the standard by which the entire idea is judged. That contradiction, an atrocious efficiency paired with an extraordinary record, is the heart of the story, and to resolve it you have to see what the machine is actually optimized for, which is not efficiency at all. Think of the difference between a machine built to save fuel and a machine built to never ever fail in a way that puts an aircraft in the water. Those are different machines. The catapult is the second kind, and it spends energy the way a parachute spends air, wastefully and on purpose, because the thing it is buying is not economy. So here is the inversion, the piece most people never hear. The steam catapult is not clever because it is powerful. It is clever because it can be finely and repeatably controlled, and the crude, wasteful physics underneath it is exactly what makes that control so reliable. The heart of the system is a pair of long cylinders running under the deck, each holding a piston, and the two pistons are joined to a shuttle, the fitting that rises through a slot in the deck and grips the aircraft. Steam is generated by the ship's power plant and stored, not used directly, but stored, in large vessels called accumulators, held there under high pressure and ready. When a launch is ordered, a launch valve opens and admits that stored steam into the cylinders, and the pressure drives the pistons and the shuttle forward, dragging the aircraft with them. And the entire art of the machine is in that launch valve. It does not simply open. It opens on a schedule measured in hundredths of a second, its opening rate metered so that the steam enters the cylinders in a controlled curve rather than a single slam, and that curve is set differently for every launch depending on the weight of the aircraft and the wind over the deck. A heavy aircraft on a still day needs a different curve than a light one with a strong headwind. The crew set that energy from approved launch data, never by guess, and the valve delivers it. The stored steam arrangement is what makes this possible, because the energy is sitting ready in the accumulator and can be released in a shaped, metered pull rather than whatever the boilers happen to be making at that instant. And notice why the tolerance sits where it does. The energy is not set at the minimum the aircraft needs to fly. It is set with margin above that minimum and margin below the point that would harm the airframe, inside a window, and the whole system is built to land reliably inside that window every time rather than to squeeze the last % of efficiency out of any single shot. The goal is not to use less steam. The goal is to never miss the window. That is why a 4% efficient machine is the right machine. Efficiency was never the specification. Hitting the window 100 times a day for decades was, and when the piston reaches the end of its run, the energy that is left, and there is a great deal of it, has to go somewhere, which brings us to how the whole ferocious business is built into the ship. Look at how the catapult is arranged in the structure of the ship, and you are looking at a set of choices about where to put the force. The two cylinders run beneath the flight deck along the launch track, and the shuttle protrudes up through a slot that runs the length of that track. That slot is a problem the moment you think about it. It is a long opening in the pressurized steam cylinders, and steam under pressure wants to escape through any opening it can find. So the cylinders are fitted with a sealing arrangement along that slot. Strips that are pushed aside by the shuttle as it passes and close again behind it, and the crucial thing to understand is that the seal is deliberately imperfect. It cannot be perfect. A perfect seal on a slot that a moving fitting has to travel through at enormous speed is not achievable. So the design accepts that some steam will always escape upward through the deck slot, which is why anyone who has watched a launch has seen steam curling up off the track. That escaping steam is not a fault. It is the accepted cost of having a slot at all. At the end of the track sits one of the most important and least glamorous components in the whole machine, the water brake. When the pistons reach the end of their stroke at full speed, they are stopped in about 5 feet by driving into a controlled body of water that absorbs their enormous remaining energy. The water brake is built to arrest the pistons even if they arrive at nearly twice their normal speed, because the one thing you cannot have is the pistons tearing out the front of their cylinders. So the force is placed deliberately. The energy goes into the aircraft, the leftover into the water brake, the waste steam up through the slot, all in directions chosen in advance. And there is one more directed energy problem the deck has to solve, because the aircraft about to launch is at full engine power while still held to the deck, and that engine exhaust has to go somewhere too. Behind each catapult, set into the deck, is a jet blast deflector, a large panel that rises hydraulically just before launch. Its job looks simple, to shield the crew and aircraft behind from the exhaust of the one about to go, but is doing something less obvious as well. The panels are actively water-cooled because the exhaust of a fighter at full power would otherwise damage the deflector itself over repeated launches, and that cooling is what lets the deck cycle a launch every 20 seconds or so without the deflector failing. It is the same logic as the water break and the imperfect seal, a component built to absorb and redirect a punishing amount of energy on every single cycle, placed exactly where the energy was always going to go. Now the components that connect the aircraft to all of this, because here is the detail to hold on to, and it will matter later. The aircraft is held to the deck against the growing pull of the catapult and its own engines at full power by a holdback fitting. And on the older aircraft, that holdback was a piece designed to break. A frangible link, a metal fitting machined with a waste at its center, calibrated to fail at a precise combined load so that the aircraft was released at exactly the right tension. One launch, one broken link, replaced by hand for the next. Hold on to that. A part designed to break that a person has to replace every single time, and what happens when the wrong one is fitted. Because the holdback is the small, cheap, human-handled component at the center of a machine that does everything else automatically. And it is exactly the kind of component that, decades ago, wrote a hard lesson into how these launches are run. Here is where the obvious cause turns out to be the wrong one to worry about. Ask what goes wrong on a catapult launch, and the mind goes to the big machinery, the pistons, the accumulator, the launch valve, some catastrophic failure of the powerful parts. But the powerful parts are heavily engineered and rarely fail. The dangerous failures cluster around the small connecting hardware and the human handling of it, and the most instructive is the failure the crews call a cold shot. A cold shot is when the catapult delivers less energy than the launch required and the aircraft leaves the deck below flying speed. There is no recovering it in the distance available. The aircraft settles off the bow, in front of a ship moving forward that physically cannot stop or turn in time. And one of the ways a launch goes wrong is bound up with that holdback fitting, the breakable part from the last section. Every aircraft type has its own holdback calibrated to release at that aircraft's correct tension, and they are deliberately made so they cannot be interchanged, because fitting the wrong one means the aircraft releases at the wrong load. Released too early before the catapult and the engines have built full tension and the shot is soft. The consequence of a small handling error on a cheap part is a multi-ton aircraft in the water. The response to this, over the history of the system, tells you how the machine really works. The frangible holdback links, the ones that broke on every launch, were themselves a hazard beyond the calibration problem. The spent, broken pieces became debris on the flight deck, and debris on a flight deck can be ingested into a jet engine, which is its own catastrophe. So the engineering answer, developed and patented in the early 1970s, was the repeatable release holdback bar, a reusable fitting using an internal locking mechanism that releases at the set load and then resets, rather than a piece that shatters and has to be swept up and replaced. It removed the debris. It removed the constant hand replacement of a broken part under time pressure. It reduced the number of people who had to be in close proximity to the aircraft at the moment of launch. Nothing in that chain was exotic, a cheap part designed to break. A person fitting it, one of hundreds of times in a day, under noise and time pressure. A calibration that had to be exactly right. Ordinary things, and the fix was not a more powerful catapult, but a smarter small part, one that took a repeated human action and a stream of dangerous debris out of the loop. That is the pattern of how this machine got safer, and it is worth remembering when we come to the machine that was supposed to replace all of it. Which brings us to the strangest turn in the whole story, the one that made news in the summer of 2026. For decades, the steam catapult's flaws were understood. It is heavy, all that plumbing and those accumulators and the water for the steam at enormous weight high in the ship. It is maintenance hungry, the seals and the valves needing constant attention. It delivers its energy in a single front-loaded pulse, hardest at the very start, which is manageable for a robust fighter, but punishing for a light airframe like an unmanned aircraft. And it wastes almost all its energy. So the Navy developed a replacement that fixed every one of those problems at once, the electromagnetic aircraft launch system, EMALS, which uses a linear motor, the same principle as a magnetic levitation train, to accelerate the shuttle. On paper, it is better in nearly every way. It is far more efficient. It accelerates the aircraft smoothly instead of in a brutal front-loaded slam, easing the stress on the airframe. It can be tuned precisely enough to launch both heavy fighters and light drones that a steam catapult would damage. It weighs less and it eliminates the vast steam plumbing. It was fitted to the newest class of carrier, and it represents a genuine leap. And yet, The specification for the system called for thousands of launches between failures. In operational testing reported by the Pentagon, it was achieving a small fraction of that, a few hundred launches between failures rather than the several thousand required. And a failure in an electromagnetic system, deeply integrated into the ship, is far harder to repair while at sea than a steam component, and a single failure can take down a larger share of the launch capability than a steam catapult failure would. The very integration that made it elegant, made it fragile in service. And so, in a memorandum dated the 13th of August 2026, the decision was taken to plan a return to steam catapults on a future carrier, giving up the efficient, elegant, smooth new machine in favor of the wasteful old one. Because the wasteful old one, across 70 years, could be counted on to launch an aircraft better than 99% of the time it was called on. The lesson is the same one the Holdback bard taught, scaled up to an entire system. The machine that wins at sea is not the one that performs best on paper. It is the one that fails least, and that a crew can fix when it does, which leaves the part of the whole system that was never engineered, because it could not be. Everything we have described, the accumulator holding its steam, the launch valve metering its curve, the water brake catching the pistons, the holdback releasing at its set load, does exactly what it was built to do and not one thing more. None of it decides. The launch valve opens to the energy it is told to deliver, whether that number is right for the aircraft sitting on the track or wrong. The catapult will fire a soft shot as readily as a good one if the wrong data is set or the wrong holdback is fitted, because it is executing, not judging. So the launch depends in the end on people, and the flight deck is built around that fact. The energy for each shot is set from approved launch data, cross-checked, because a mistyped weight is a cold shot waiting to happen. The catapult officer, the shooter, sits in an armored control station with a view of the deck and makes the final decision to fire only when the aircraft, the deck, and every check are confirmed. And the deck itself is one of the most carefully choreographed and most dangerous workplaces in the world. A space of moving aircraft and jet blast and cables under enormous tension, where every person has a specific station and a specific set of signals, because the machinery gives no warnings and forgives no wandering. That environment does its own work on people. The noise is constant and enormous. The pace during flight operations relentless. The margin for a lapse essentially zero. And the design accepts this by making as much as possible automatic and by drilling the human parts until they are as close to automatic as a person can be. But the last judgments cannot be automated. Someone confirms the weight. Someone fits the correct holdback. Someone looks down the deck and decides it is clear. The honest pattern, the one the cold shot and the holdback and even the story of EMALS all show, is that the catapult's worst days come not from the great machinery failing, but from a small part, a wrong number, a mischeck, an ordinary human error at the connecting points, and the defense against that is a crew trained to treat every launch as if it could be the one that goes wrong. The machine displays and it fires. It does not conclude. The concluding is done by people on a steel deck in the wind in the seconds before a jet is thrown at the sea. So count the four again, quickly, the way they actually stack. The launch demands a precisely metered burst of energy tuned to each aircraft, not merely a lot of it. The steam system meters that energy through a valve timed to hundredths of a second, buying control with an efficiency that would be unacceptable anywhere else. The whole ferocious business is built into the ship with its waste directed on purpose, its leftover energy caught by a water break and its steam vented through a slot that can never fully seal. And the machine built to replace it, better in nearly every measurable way, was sent back in favor of steam, because reliability at sea beat efficiency on paper. 4 systems, and the 5th thing we named at the start, now, has a face. It is the crew who set the number and fit the part and decide the deck is clear. Go back to the image we opened with, a fighter thrown off the bow in 2 seconds by a machine that wastes almost everything it burns. You can see it differently now. That waste is not a flaw the engineers failed to fix. It is the price of a machine that hits its window every time, in salt and vibration, for 40 years, and can be repaired with tools when it does not. The Navy built the efficient machine, the smooth and elegant one, and then chose the wasteful one that fails less. That choice is the whole philosophy of the thing in a single decision. The catapult was never trying to be efficient. It was trying to never put an aircraft in the water, and to be fixable by the people standing next to it when something finally goes wrong. If you want to keep going inside machines like this one, the ones almost no one is allowed near, that is the whole reason this channel exists, so subscribe and stay with it. The next one goes to the other end of the flight deck, into the arresting gear that stops a landing aircraft in the length of a tennis court, where the strangest part is what happens to the cable itself over the course of a single day, and why a component that looks like simple wire is one of the most closely tracked parts on the whole ship. And a question for the comments while you sit with this one. If the Navy built a machine that was better on paper in almost every way, and then chose to go back to the older, cruder, wasteful one because it failed less often, was that a step backward, or the most sophisticated engineering judgment in the whole story? And are those really different things? There is a real argument on both sides, and I would like to read yours. This video is for educational purposes only. It draws on published engineering literature, declassified documentation, manufacturer and service publications, and investigated peacetime incident reports. Where a figure is an outside estimate or has never been released, this is stated, and where practice varies between services or jurisdictions, this is noted. Nothing in this video is operational guidance.